So just to contextualize where we are, yesterday I spoke about the larger problem of probabilistic generative modeling, and I pointed out that usually we're trying to model data that's quite complex with many different parts, and there's relationships between them, and we can usually break those down into subcomponents, and then we are interested in modeling the various smaller components, and sometimes we might have latent variables, in the case of VAEs, for example, where we reduce dimensionality, but ultimately at some point we might get to some collection of variables where we don't have any real intuition or structure or knowledge about what that density or distribution looks like, okay? And that means, for example, we don't have a good idea of what parametric form to use. We don't really know where to go. And that is a good place to think about using normalizing flows. Because normalizing flows you can think of as a general way of learning a density. Okay, so we go, and the idea with much of the research is to broaden the collection of models that we can use to learn these densities. And the different classes of functions that we consider are going to have different benefits and different costs. So there's always a cost-benefits analysis that you have to do when you're choosing between the various approaches that are available. And so ultimately, getting familiar with the different approaches and how they work and what their position is in this cost-benefit trade-off is part of getting really good or comfortable in the normalizing flows space. Okay, so then we spoke about normalizing flows, and the way we built normalizing flows was to have a base distribution, which we always were using the variable z for, and the data distribution, which we use a variable x for, and the idea of the model was that we were going to have some transformation t that goes from the base distribution to the data distribution. And we require that this transformation t is something that we can invert so that there's a one-to-one mapping between values in the base distribution or the domain of the base distribution and the domain of the data distribution. And this requires that those two variables have the same dimension. Okay. We also, because we want to use the change of variable formula and we want to use automatic differentiation and all these things, require that this transformation be differentiable. And its inverse needs to be differentiable. Okay. And once we have that it is differentiable, then we can apply the change of variables formula in principle. Let me try and find, no. We can apply the change of variables formula to say something about the density of the data distribution based on the density of the base distribution, and this log, this determinant of the Jacobian. Okay, so this determinant of the Jacobian is an important thing for us to be able to work out. We want to be able to figure this out for points in our training set when we train our model as well, and so it's very important to choose classes of functions where this is efficient. Okay. If it's quite common to, instead of working with this product form, to work in the log domain where these things decompose nicely into sums, and we also usually will take this complicated function t, and the way we will build it up is just like with neural networks, by composing a number of simpler functions which will be nonlinear. And so when we do that and we use the fact that the Jacobian of a composition of functions is the product of the Jacobians, we get this formula over here, that the log of the data distribution density is the log of the base distribution density with a bunch of terms added, which are logs of absolute values of Jacobian determinants. Okay, so that is the mechanism that we want to use. We could also, instead of using the Jacobians of these FKs, which are going from simpler distributions to more complicated distributions, use the FK inverses, which go from more complicated to simpler. And so sometimes, even though we know these functions are invertible, they're not easy to invert in practice. Okay? And so sometimes we have to decide, are we going to implement the function that goes from the simple distribution to the complicated distribution, which is helpful when we want to sample, Or are we going to implement the function that goes from the complicated distribution to the simple distribution, which is helpful when we want to do density estimation because we're going to get something in the complicated distribution and we're going to want to know what in the base distribution corresponds to it. So we can either make one of those two directions efficient and sacrifice our ability to answer the other problem efficiently, or we can have a constrained capability of our functions, less expressive, but be able to do both of these fairly efficiently. Okay, so that was kind of where we were at the end of the last lecture. Oh no, okay, we actually also did a little bit more. We spoke about forward versus reverse KL divergence, but I'm going to not talk about that. And then we started speaking about the first class of flow types there, autoregressive flows. And this was kind of an illustrative example of something where we can do efficient forward implementation, so from the base distribution to the complicated distribution, but inverting it is slow, but we can get the Jacobian determinant efficiently because we use this autoregressive structure. Because the autoregressive structure, we get a triangular Jacobian. That means that the determinant is the product of the diagonal entries, and so if we can compute those diagonal entries efficiently, then we can work out the Jacobian determinant efficiently. And in order to get those diagonal entries efficiently, we make our transformations that we're applying component-wise affine transformations, because then that factor is very easy to obtain. Okay, and so in this situation, we are transforming each component using this affine transformation, and the parameters of the affine transformation we're getting from the earlier components. That's why it's autoregressive. Those parameters over there include the scaling factor that we use. And that scaling factor is exactly the thing we need for the Jacobian determinant. So we're getting it out as part of the computation. So we can not only do the forward pass, we can also extract the Jacobian determinant as part of the process, and that's going to allow us also to do automatic differentiation in order to fit our model. Okay. Now, this setup, I pointed out that you could work out each component in parallel of the output of this flow by taking a specific element and pushing the previous components in through this conditional network. But you can do that for every component in parallel. And either you can have a separate conditioner network there, or you can share weights, and you can do various things there. But when you want to invert it, unfortunately, it's slow. You've got to go back. You've got to go element by element by element and invert each element so that you can use it in the conditioner network. Okay, so one way we looked at to alleviate that was using coupling layers, which is what they use in something called real NVP. And that makes the transformations much less expressive, but it makes the forward pass and the inverse, the forward and the inverse transformation cost the same thing, which is very helpful if you are confident that you need to do density estimation and you need to do sampling. Okay. Another trick you can use is you can simply say that I'm going to let this tau, instead of depending on the previous components of the z's, I just let it depend on the previously computed outputs. So in other words, Ci is going to take these values at the top. Okay? In that case, I will have to work out these elements one by one by one. So the forward pass will be slow. I'll have to do them in series. But a nice side effect of that is that the inverse is going to be able to be done in parallel. So this means that we're going to have a slow training phase, but when we're finished, we can do sampling very efficiently. Okay, so that's called inverse autoregressive flow. Okay. And that is where I said we've covered the essential concepts underlying normalizing flows and wrap things up. Okay, so now what we're going to do is we're going to look a little bit more at some of these other flows here, just to give you a flavor of what people are doing in this space. And then maybe if there's time, we'll dig a little bit into the VAEs and how we use these flows there as well. But the short version is that latent distribution, you fit a flow to that because you don't know anything more. instead of using a Gaussian. That's the naive first thing that you can do. There's a bit more, but that's the basics. Okay, so 3 things: expressivity, efficient evaluation of the Jacobian and or its determinant, and efficient evaluation of T from T inverse. In other words, flow inversion. Okay, so in terms of expressivity, as you add more layers, in general, not in all cases, more layers means more expressive transformations. Okay? Mathematically, you can prove universality arguments, which say that if you have enough layers, you can approximate any density with certain types of flows and that kind of stuff. But generally, in practice, you want to put in enough layers so that you can get good performance. If you put in too many layers, it makes it hard to train. It makes it slow to train. It makes it numerically unstable. So you don't want to put in more layers than you need. But if you put in too few layers, you're not going to get good performance. So it's a bit of a hyperparameter optimization factor. That's all I'm going to say about how many layers. Okay. In terms of efficient computation of the Jacobian determinant, the Jacobian is a D by D matrix if D is our dimension. Inverting a matrix like that in the general case is typically, calculating the determinant is cubic. Cubic is too slow, so we want systems which are much faster. Typically, we want them to be linear. Linear in dimension for high dimensions is what we will generally consider tractable. You can do just about nothing in a sublinear setting. Quadratic is slow, but usually kind of doable, and cubic is just off. Okay, so we need to find tricks to train in linear time. That's important. We can't be training in quadratic time. Okay. Now, we've already spoken about building a triangular Jacobian. If you go back to this coupling layer idea that we used before, and you pay attention to this, you'll see that the left-hand part that we passed through unchanged, over there, if we just composed a number of layers like this, the first half of our input would never change. So we would never learn anything sensible for the first half of our data. It would always stay the base distribution, marginalized to those components. So when you use coupling layers in things like nice and real NVP, there's an additional permutation step or a switch step that happens where you simply reorder your variables between each layer. Okay. That reordering of the variables is a permutation. Okay. Now, a cool thing about a permutation is it is a transformation. You can write it down as a matrix. It has a Jacobian determinant, and the Jacobian determinant is either plus or minus 1. Okay. Which means that if we add it in as a transformation, it doesn't change the volume. We don't have to worry about it. Downside of a permutation is we have to decide what permutation to apply. We have to kind of hard code it. Because moving from one permutation to another isn't a continuous thing, you can't optimize that with gradient descent. You can generalize permutation matrices. They're a special case of orthogonal matrices. Okay, so we can use orthogonal matrices as a transformation, and an orthogonal matrix by definition is one that has a determinant of 1, or very close to by definition. Okay, so we can rotate effectively and reflect our data however we want from one layer to another without warping the data size, and that can be useful for entangling the components and so on in useful ways. And we can train how we do that. So orthogonal transformations, these switches that we do in these coupling layers, and permutations in general are all what are called volume-preserving transformations. We can transform with these things, we can invert them if we design them to be invertible, and we know that the Jacobian determinant is going to be 1. So we don't need to keep track of it, we don't need to optimize it, it's going to be 1. So they are very easy and helpful things to just slot in where appropriate in your chain of transformations that you want to apply. So we've got that. The second thing is using triangular Jacobians, which we've spoken about a fair amount already. But sometimes you could, autoregressive flows are universal. If you have enough layers, you can map any density. But you need quite a few layers. So the question is, if we can have fewer layers that we can perhaps train more efficiently, that are more expressive by using more sophisticated math. That's basically, the arms race here is to use more sophisticated mathematical and estimation techniques so that we can use more expressive layers, so we can use fewer layers, which allow us to train more efficiently and sample more efficiently. Okay, so the first tool we get here is something called the matrix determinant lemma. Now, the matrix determinant lemma tells us how to get the determinant of a certain kind of matrix. Okay, and this determinant is called, this kind of matrix is called a rank M update. Okay, so basically what we're doing is we're taking the identity matrix and then adding a little bit to that matrix, and the changes we make to the identity matrix is a low rank matrix. Okay, and in that setting, the rank of the change we make can be used to improve the complexity of obtaining the Jacobian determinant. We're not going to go into that, but basically, in that setting, we can rewrite the matrix from a D by D matrix that we want to find the determinant of to an M by M matrix. And an M by M matrix, we can find the determinant of in time M cubed, not D cubed. So if M is small, M cubed might be tractable. Okay, and to do that change is going to take us time order M squared times D. So this is linear times something small, and so ultimately this can be efficient. The question is, how do we choose M? So some of the earliest flows, planar flows, used a rank 1 update. So M here was 1, and that was very efficient, but that limited the expressivity. If we can make M a bit bigger, we can get a more expressive thing. So now we have a trade-off. We can use higher rank updates of the identity matrix for more expressivity at the cost of more cost computationally per layer. And when we start using higher rank updates here, we get something called Sylvester flows, which also came out of the same Max Welling's lab, where the VAE, well, one of the birthplaces of the VAE. So there's a lot of activity in that space over there. So I'm not going to go into exactly how we know that this is a rank M update and so on, but what I want you to note here is that there's a common neural network architecture where you're going to get a Jacobian that looks like the identity plus something, and that is a ResNet. Okay, now if you've got a ResNet with a number of blocks or a number of layers, each layer is updating its input, or the output is the input plus some transformation of the output. And that extra bit we add there, that component is called the residual block. And so the Jacobian of the output is going to be the identity, because it's keeping this, plus the Jacobian of this G. Right. And so when we design effectively something that looks like a residual block that has a low rank effectively, then we're going to be able to use the matrix determinant lemma. And so actually, if you just use an MLP for your residual block and you use the MLP as an autoencoder, or not an autoencoder, a simple one-layer neural network that has got a bottleneck layer in the middle that is with M, then you're going to get a rank M update. Okay, so if it's a rank 1 update, there's one hidden node in the middle layer. If there's M hidden nodes, then it's a rank M update. And so you can control it by just modifying the dimensionality of that residual block. But that limits you to using a very simple MLP structure there. And further work, it works on, can we generalize what that residual block looks like? And that's the last part I'm going to talk about, contractive residual flows. Okay. So the key part for contractive residual flows, and I think this is a very exciting idea, is that when we're fitting with a neural network, we're using stochastic gradient descent. And stochastic gradient descent is stochastic optimization. We need to move towards the optimum, but we are using sampling in many cases. So we just need to get unbiased estimates of the thing that we're trying to move to. We don't need to get the actual thing. So the key is to try and get an unbiased estimate of the Jacobian rather than the actual exact Jacobian. And so what the space of contractive residual flows is looking, or the techniques that get used there are about estimation of the Jacobian determinant as opposed to exact computation of the Jacobian determinant. Okay, note that for ResNets to be, I just said, hey, let's use a ResNet architecture, but remember that our transformations need to be invertible. Okay. If we want a ResNet to be invertible, we have to constrain this G in some way. We need to make this residual block what we call contractive, which means that if we push in an input into that little network, the output, the distances between outputs has to be smaller than the distances between inputs. If I give two inputs in and they have a certain distance apart, and I look at the outputs, they need to be closer together. Okay. This kind of prevents the residual block overwhelming the identity when we are trying to enforce invertibility. Okay, so that you don't get results that are on, and say that's what we're trying to do. Okay, so we're going to constrain G to be contractive, and practically what we do there is we use spectral normalization of the MLP layers that we're using, and then we use very particular activation functions, but the simplest one that will work is like the tan H, that's well known. Okay, if we use those, then we're going to get these contractive residual blocks, which gives us an invertible residual network, and the last component for contractive residual flow is estimating the log Jacobian determinant. Okay, so I'm not going to go into all the detail, but there are some key ingredients, so this just gives you a flavor of all the moving parts that go into trying to estimate this. So the first thing is a bit of matrix calculus. There's a matrix calculus identity that says that if a matrix is invertible, then its log determinant is equal to the trace of its log. Okay, so this is the matrix logarithm. And the matrix logarithm can be expanded with the Taylor series. Okay, it's the same Taylor series that you use with the regular log of 1 plus x. It's exactly the same pattern we're using there. And then we are taking the trace of that sum, which becomes the sum of the traces. So in the end, we try and compute this thing, but this is an infinite sum. We can't work out infinite sums in finite time, so that's a bit of a problem. But let's just consider a specific term in this. Well, minus 1 to the power, that's easy. Dividing by k is easy. We want the trace of this power of a Jacobian. That's a bit more involved. And if you're paying attention, you'll say, hey, but we don't want to work out powers of Jacobians because that's expensive. Okay. But what we're going to do is we're going to replace each of these traces by this thing called the Hutchinson's trace estimator, which is an expectation here. So, and this is an expectation where this comes from a distribution we can sample from. So we can use Monte Carlo estimation to do this when we plug it in over there. And what we're doing is we're taking that big matrix and we're reducing it to a scalar by multiplying by the vector on either side. So instead of actually working out this power, we work out the power but starting with a matrix, multiplying it by with a vector, multiplying it by a matrix, which is fast, and then we take the resulting vector, multiply it by a matrix, which is fast, and we do that repetitively. So we never have to work out this power explicitly. And then what we also do is we share these computations by reusing these sample values for different terms in the sum. Okay, so that introduces some bias, and so by using the finite sum and this reuse, we got this bias, and then there's this adjustment called Russian roulette estimation, which allows us to reweight these terms and truncate the power series to get an unbiased estimate. So there's a lot of moving parts. Once we've got that unbiased estimate, everything there can be computed efficiently. We can add it all into our objective, and then we can use stochastic gradient descent. And everything just runs neatly on its own. Now, this takes some time to get around, so until you can use it if you get the right library, but if you want to go do it yourself, this is not a good place to start. Okay, start with the earlier ones first. Okay, so that's quite a bit on log Jacobian determinants, but it's showing you that there's quite a lot of interesting research happening here that's leveraging interesting maths and estimation theory in order to allow us to broaden the collection of functions that we can use for normalizing flows. Okay. the last part I want to talk about is flow inversion, because now we can work out the log Jacobian determinant, and if we design things so that we can compute the inverse transformation efficiently, we can train our network neatly and efficiently for density estimation with maximum likelihood, or if we can implement the forward transformation efficiently and we can compute the unnormalized density, we can use the reverse KL divergence to fit this model for sampling. So those are the two options. But then ultimately, we need to sometimes invert this flow. So if we make the flow easily invertible from scratch, we can do both tasks easily. So that's not a big problem. But if we have an expressive, complicated model, we need to think about how to invert it. And one approach is numerical inversion. So numerical inversion has got its weaknesses. It's usually an iterative technique. It can be fairly slow, but it gives us a way of getting the inverse at least. So when it comes to numerical inversion, we would like reliable convergence to the right inverse. We would like it to be numerically stable, and we would like to take few iterations and for each iteration to be fast. Okay. So if we just think about inversion, analytic inversion first, before we talk about the numerical approaches in more detail, if we had a general linear transformation, full rank, okay, and that was the transformation we wanted to do, and we wanted to invert that, that's cubic. That's why we don't use plain linear transformations. Orthogonal transformations are fine, by the way, because they are easy to invert, because we just transpose the matrix to get the inverse, right? But for general linear transformation, we have a problem. If we use triangular transformations, with, if we use basically autoregressive transformations, then inverting them is quadratic. That quadratic cost is the reason why when we try and invert the autoregressive flow, we need those many serial operations. That's the problem manifesting in our implementation. In terms of numerical inversion, there are two main approaches that get used. Okay, so the general approach is something like Newton's methods, quasi-Newton methods. Okay, so Newton's method requires us usually to invert the Jacobian. Okay, that's not usually very tractable. So we want to have something close to that, and so the approach that's popular, that was proposed by Yang Song, who's also involved in the work on diffusion models, score-based models, is we simply use the diagonal of the Jacobian as an estimate of the Jacobian and invert that. Okay, so there's a Newton-like method, and it can be shown that under certain conditions, this converges locally, and so we can use it, and it's nice and fast because it's linear to invert that. Right. A more general approach, a more theoretical approach that works globally is something that uses something called the Banach fixed point theorem, but that only applies to the residual flows. Okay, so there are these two approaches. We get guaranteed convergence from the Banach fixed point theorem, but only for residual flows, or you can use Newton-like methods, which are fast when they converge, but it's not guaranteed. Okay, I've got a little bit of time left still to talk about flows for VAEs, but before I go into that, I just want to give an opportunity now to ask about any questions about flows in general that you'd like to ask. I think there's a good time before we delve into this. I'm going to be very quick on the VAE stuff. Yes?
For like considering the contraction of the space just locally, for example, just along some components, or like, what's the, I didn't get exactly what is the part that makes completely intractable the flow in case of non-invertible, let's say, transformation. Or
Okay, so the assumption right from the beginning, sorry, the question is basically why do we need the flows to be invertible, the transformations to be invertible? Okay, so the essential definition of the flow is that I'm able to associate any particular point that I observe in my observation space with a unique point in the base distribution. And so I can go from any point in my base distribution, likewise, back to a unique observation. Okay, and if you think about this from the perspective of z's being latent variables that you're not observing, and x being observed variables, then this is saying that that you can always do exact inference. You can, for any x, there's an exact z that you know that corresponds to it. Okay, and so that is the way we design this. But when we have that these two points correspond to each other, we can still get warping of the density, or even just compression, like we did with the scaling example. And so we need to keep track of that so that we get the right densities in the base distribution relative to the data distribution. But the requirement for invertibility is basically to allow us to uniquely associate a base distribution point with a data distribution point. Okay.
Requirement is for density estimation, right? If or sampling.
The requirement is for density estimation and for sampling.
Okay, so for example, like for dimensionality reductions or something where we actually want, let's say, to compress the original space. It's,
Okay, so when we want to do dimensionality reduction, we can't use a flow directly. Okay, because the flows are using an invertible transformation where the dimension of the data and the base distribution are the same. If you want to do dimensionality reduction, usually you are going to be using a latent variable model where you're going from observed higher dimensions to latent lower dimensions. And then once you do that, you might be interested in the distribution of those latent dimensions. And there you could fit a flow to those variables. Okay, and that's actually one of the things we're going to do with the flows for VAEs. But the invertibility requirement effectively locks you out from dimensionality changes. Okay, all right. Any other questions? Okay, so Xavi and Matthias, and I don't know if anyone else, have already discussed VAEs in a fair amount of detail. I have some slides here which look at it from perhaps a slightly different perspective, but I don't think we have time to go into it, so I'm going to fly through it. I use a lot of the viewpoint of Bayesian networks to try and explain things, and I might have to refer back to one of them as we go along later on. But key thing, we have latent variables in a variational autoencoder, and to fit it, we would like to maximize the marginal likelihood. Okay, we can't optimize the maximum marginal likelihood exactly, and so we use variational inference, where we would like to optimize the KL divergence between the true posterior and an approximate posterior. We can't do that exactly either. So we throw away a little bit of an awkward term, and we're left with the elbow, the log evidence lower bound. Okay, so that's the situation. We want to do our variational inference by maximizing the elbow, and general variational inference tries to do this when you know what your generative model looks like. Okay. With a VAE, the interesting thing is that you are trying not just to do variational inference for a known model, but you are also trying to learn the model at the same time. Okay, and the traditional way of doing that before variational autoencoders was something called variational EM, variational expectation maximization, where you, roughly speaking, alternated optimizing the generative model and performing inference. You did them step by step by step by step. Okay, and you can think of the VAE as essentially interleaving those steps very finely. Okay, so that you're busy updating your model and updating your inference network in parallel, and we do that end-to-end with an autoencoder-like architecture that we train with SGD. Okay, so that's the viewpoint that we're using. But it's important to remember that ultimately, we've got these two components. The one is the generative model that starts with a latent variable and then transforms it to an observation. And this distribution X has got typically just this transformation is parameterized by theta from your decoder. And then we've got the inference network, which is trying to construct Zn. And when we're using amortized inference, we are determining Zn based on Xn by computing the variational parameters for Zn by using a network with parameters phi 0. Okay, so phi 0 is our encoder network weights that we plug Xn in to get the parameters of the latent variational distribution phi n that we use to sample the latent variable Zn. So that's how all these things hang together. Okay, and this is what it looks like architecturally. So that was the very high-level view. Questions on VAEs before I dive into how we can use neural net normalizing flows in that context? Okay. All right, now, I've mentioned that the VAE is learning the generative model at the same time as doing inference. So the question you might ask yourself is, if I learned the generative model with variational autoencoders, how would the generative model parameters look if I compare them to what I would get if I actually maximize the marginal likelihood without using variational inference? Okay, so the one optimizes the elbow, that's the tractable one, and the one optimizes the log evidence, okay, which is the intractable one. Now the log evidence, if we assume IID observations, decomposes across each observation, so we can think of the log of the density of each observation, and we can consider this on a per observation basis. So let's suppose that we have chosen some variational parameters, phi. Okay? Now this phi might be at its optimal value or some other value that it's at during training or whatever, but let's just assume it's fixed. Okay? If we know that that's fixed, we can rewrite the elbow and also decompose it across all the different observations. Okay, so in that case, we can look at how do these two things compare to each other. Okay, and this is an illustrative diagram, and it's showing that there's some true log marginal likelihood, and what we would like to do for a fixed value of the variational parameters is find the optimum value of the red curve. Okay, but what we actually do is we take the elbow, which is like diagrammatically represented by the blue curve here, and we try and find the theta that optimizes that. Okay? And that's fine when they have their maxima close to each other, but sometimes they aren't. And the looser the elbow is, that's why the slide says the dangers of a loose elbow. The looser the elbow is, the more likely that the peaks are not going to be aligned as well as they should. Okay, so we really would like our elbow to be as tight as possible as much of the time. We want to throw away as little as we can, and one way of doing that is to make sure that this variational family that we use is rich, so that the closest point in the variational family to the true distribution is close by. Also, with the VAEs, we're going to see this in a little while, is there's a way of kind of making your density, your distribution somewhat simpler and closer to Gaussian, and then the flows may not help you so much. I think also that they are not quite as new as VAEs, and someone was asking about the more complicated math, right? You need to know about the different specific, you need to know about a specific type of flow and say, okay, this is going to be appropriate in this case. But I think it's also just a case of it's becoming better known over time. But at the moment, I think that it was moving in a certain direction, and that direction has, for example, also led to things like, or I think it was one of the catalysts for things like ordinary score-based models and diffusion models. A lot of the same thought is going into developing all of these, and at the moment there's research happening in all of them, and we're trying to see what's going to work the best. Yeah, so that's just a bit of hypothesizing. Okay. Any other questions? Okay, so luckily I've got that extra hour of lunch that I can use still. So I mentioned earlier, or this looseness that we had over here, okay, is all about the so-called approximation gap, which Matthias mentioned before, okay? This is saying I'm going to estimate the wrong thing here because the elbow doesn't match the maximum marginal likelihood. But there's also the amortization gap, which says that even though I could do this for each point, I actually am trying to learn a network that predicts this value for all my points. And so I'm not going to get the exact right point for each one. And so I'm going to get another bit of weakness here where I might only predict this instead of that. And that's the amortization gap. So we got these two sources of looseness, and what we'd like to do is we'd like to reduce the approximation gap. That's the one thing, which means use a larger class of networks, but we also want to reduce the amortization gap. We want to be able to predict better. Okay, we want to make better predictions in general. And one way of perhaps doing both of those is considering bigger networks for our variational inference, right? That gives us a bigger class of networks, and maybe we can train them to predict better. Okay. So our aim then is to enrich the variational family, which reduces the approximation gap, but we want to enrich it in a way that keeps the amortization gap small. Okay, so we don't want to make it that it's we make a very big network and then we can't fit it well. That would not help. We want bigger, better networks that we can still train well. Now, how do we choose to enrich this variational family? Well, okay, if we still want to use mini batches for training, like we do with the VAE, and we still want to use amortized inference, then we've got to be able to decompose our elbow across observations, and that basically means that we have to use something like a mean field variational family. But within any particular observation then, we've got a general modeling task for the posterior. So we've got this posterior that we don't know, the true posterior. It's a distribution. We don't know anything about it. That's exactly where we want to use normalizing flows. Okay? You could have assumed it has a parametric form. You could, and that's exactly, by the way, what we do with the regular VAE. We assume it's a Gaussian. There's the mean, there's the variance. Try and estimate those. Okay? But we could assume that it is a flow. It's a more complicated distribution. That is the work that really introduced normalizing flows to the scientific community, was this proposal to use normalizing flows to enrich the latent space of a VAE. Okay, so the key thing in this situation is that we want to use it for sampling, because ultimately our VAE, we sample by sampling from the base distribution and then running our generative model. So the distribution we fit in this context has to be something that we can sample from. That's the one side. And you might think, but we also need to do density estimation for training. But because we are training with the elbow, which is in the reverse direction, we're okay. We don't need density estimation to be efficient. Okay, so that is very helpful because it means we train these things with the reverse KL divergence, same as the rest of the VAE. Okay, so just to give you a bit of a feeling for why we might want to do this, here are some example situations of what a true posterior may look like. Okay, if we could optimize each posterior, if we assume that the variational distribution was a Gaussian for each of these and could optimize them separately, we might get something reasonable for many of these points, but it would not work for this example here, right? Because it's bimodal. Okay. It would be more difficult if we needed to predict all of these different points with amortized inference. So then it might work well for those two, and fit one of the modes here, but it's off in this example. Okay, so that's a failure of amortization. If we assume instead of the fact that these are factorized Gaussians, we assume that they flows, well then we can do fine when they are Gaussians, but we can also do fine in the bimodal case. So we are now, okay, so you could say, well, I could use a mixture of two Gaussians there, but then you have problems trying to integrate that into larger systems. Okay, so this motivates the idea of let's assume perhaps that these posteriors we're interested in can be modeled by flows. Okay, now, it's one thing to say, let's just assume it's a flow, but how do we integrate that into actual implementation? Well, the answer is that we almost get it for free because we just leverage the reparameterization trick. Okay? The reparameterization trick is designed to say, hang on, I can't do the sampling in the direct flow of the computation because then I can't do backpropagation. So how do I get the Gaussian sample that I want? I sample from a standard Gaussian and I transform it. That sampling from a base distribution and doing a transformation is just a simple normalizing flow. So all we do is we sample from a base distribution and transform it in a different way to get something that's not a Gaussian. Okay, and that gives us the possibility to model all sorts of complicated latent distributions. Okay, and we can make these things conditioned on the input. Okay, so this is just going through the reparameterization trick. And when we finished with the reparameterization trick and we draw what the Bayesian network looks like, and I'm not going to do it right now, but if you download the slides and you go back to the picture I drew right near the start of the normalizing flows section, I said, here are normalizing flows, here are conditional normalizing flows. This is exactly the same diagram as a conditional normalizing flow. Okay. So our inference network, yeah, is a conditional normalizing flow because it generates observations which are transformations of a base distribution, and the transformation is determined by the thing I'm conditioning on here. So I'm conditioning on xn to get a distribution over Zn, and I get that by transforming from my base distribution where I sample epsilon from. Okay, so this can be implemented in two different ways. I'm not really going to go into the second way because of time. But for the first way, this is basically what happens. Okay? I plug in my observation. It goes through the inference network. What does it generate? It generates the flow transformations that I'm going to use. I sample from my base distribution, and I apply the transformations. This is exactly the same as I output a mean and a variance, I sample from a standard Gaussian, and I apply an affine transformation. It's just a more complicated transformation, which means that the distribution over Z that I get here can be more complicated. It can more closely fit the true posterior. Okay, I don't just want to make it complicated for nothing. I want my variational distribution to be richer. Okay, once I've got that distribution there, that corresponds to distribution, but I actually have a sample that I get from the reparameterization trick, and I can push it through my generative model, and then I can do end-to-end training with the regular VAE infrastructure. Okay, you can also do a different approach where you condition on a representation of the observation at each layer, but I'm going to skip that, and then just mention that when we do this, at least for some early examples, it turns out that the parameters we use to increase the flexibility of the approximate distribution, in other words, when we try and reduce the approximation gap, these more complicated networks actually allow us to also generalize better, and so our amortization gap decreases significantly as well. So overall, we get a dramatic improvement here from this large reduction is only actually slightly attributable to the richer variational family, but largely attributed to a better ability to generalize. Okay. The last thing I want to mention, and this has gotten a lot less attention, but I think it's quite valuable, is that it's worth knowing that when you are trying to make your true posterior distributions complicated, there's according to your training set, you can think of the average true posterior over your training set should correspond to your prior. It's a Monte Carlo estimation. It's a Monte Carlo estimate of your prior. So if you take what's called the aggregate posterior, this average true posterior or variational posterior that you're getting, and you compare it to the prior that you're specifying, your system, your model, when you fit it, is going to try and make them look the same. So if you're saying, let's make the true posteriors complicated, but I'm going to keep my prior simple, you get a bit of conflict. Okay? And that leads to something called the prior hole problem, where optimization becomes difficult and latent space is less interpretable. And a simple solution for this is to, if we just look over here, we add to our generative model a flow. So we make our prior more complex so that it can match the average of a number of complex distributions. Okay. This allows our latent space to take on more structure so that we can potentially get something that's more interpretable. Okay, so this is from one of my students' work, and this is just showing how when you try and fit a vanilla VAE, this is the prior, but this is sort of the aggregate posterior, and there are 5 underlying classes for the data here that are going on. And we struggle to kind of get them to match up, and there's a lot of overlap and so on. The second column here, we've introduced a flow for the latents, okay, but not for the prior yet. And what happens now is that we get we do get a nice separation of our observations, of our different classes in the setup, but the organization is a bit haphazard. When we allow our prior to be learned, we can allow the prior to be more complicated, and that allows us to have, in this case, this structure that separates out the different classes. So this is the underlying base distribution of the prior. This is what the prior actually looks like after it's learned, separating those different classes out, and our posterior is now able to neatly match that up, and in this case, we can maybe think of each axis as having an interpretation and so on. Okay, so I've gone a little bit over time. Sorry about we started a little bit late and we had some other technical things. I'm not going to go into the relationships between normalizing flows and VAEs beyond to say, if you're interested, go look up survey flows. They kind of they integrate VAEs, diffusion models, and normalizing flows together. So I think it's a very interesting framework for people to be looking at. But I think that's a good place to wrap up. I want to thank the organizers of the Machine Learning Summer School for inviting me to come speak with you. I hope you found some of it valuable. Also various people that I've spoken to in the past that have helped me develop my understanding of this material, and Willem for the technical assistance with Beamer. Any questions to wrap up? Thank you very much for your attention.
Any questions? Okay. If we don't have any questions, then let us thank Steve again. This was the last of his 3 talks in this series. So thank you very much, Steve. We really appreciate that. Then we'll break for lunch.
Thank you very much, and I will be around at lunch if you want to come speak to me about anything. All the best for the rest of the time here.